Hello, and thank you for joining me for the ninth data analysis bootcamp class. Okay. Uh, so this one we're going to talk about this. It's so important to understand this concept. So, we're going to explore hypothesis testing, but using hacker statistics. Okay. I never really understood hypothesis testing until I understood this, and you can really just see why and how it works and why we need it. But it's a really important concept to understand because we have randomness baked into every data set that we collect because we never collect the population. And so we always have a little bit of random effect of this sampling included in our data. We really need to appreciate that in our data analysis. Okay. Before we get started with our data analysis class number 9, let's go recap the mnemonics from the last class. Okay, so in our last class of uh, in our 8th class of the data analysis bootcamp, we discussed the histogram plot in Plotly, which, as I said, is just a really kind of cool. Lots of the things that you can do with it. One of them being you can decide instead of having each bin being filled up with the count of data that you see, you can have it being filled up with the average, median, max of another column and really start to inspect that bivariate relationship in really a way that's kind of unique. You can also, a feature that I love is that you can put the box plot with a very simple calling the argument on the top that allows really for you to, if you're in a truncate or treat your outliers, it allows you just to quickly understand exactly at what level you should be able to do. So it's a good time saver as well to use this histogram plot. Okay. We also then discussed the violin plot, and although I did mention that I like the Seaborn version a little bit better, I think that one thing that's cool here is that we can stack these plots on top of each other, layer them, so that we can really start to just really highlight what's different about each one of these distributions. Okay, so we discussed the Seaburst plot. Okay, the Seaburst plot is one of the few plots that allows you really high level detail understanding of your categories. It's really good for categorical analysis. Okay, they just it seems to work well in the sense that you're able to do the hierarchical groupings and really understand of this category what's also included in the next level, what proportions of this other category are in this one, how what is the interaction between these two categories. And that is truly a really important thing. It's not something that you can do really in any other way except for in the tree plot we talked about that allows us to really group, gives us more space versus the sunburst plot. We can still go pretty deep into it and understand a lot of extra detail and explore our data a little bit further like we can with the seaburst plot. Almost more with the tree map. The tree map works good when you have lots of classes in your category and you need to um, group them by those classes. Or so you have so many classes in your category, you just need lots of space for them to all group, all fit in the plot, so you can kind of analyze them still. Okay. We also discussed the heat map plot or the density heat map plot, which allows you to, along with the density contour plot, allows you to explore the bivariate relationship, especially useful when you have lots of data and really understand what's supporting the trends that you're seeing. A really cool feature about the heat map plot is that it allows you to do the marginal X and marginal Y across the top and the side to really give you, you can do a box plot, a histogram to give you a better sense of the data, making it almost like the joint plot in Seaborn. We also discussed, I think I mentioned this is one of my favorite plots at this point is the 3D scatter plot with Plotly. Not only because it's cool, I thought it was just going to be cool, but it actually allows you some really detailed analysis that because you can pivot around and kind of walking inside your data, you just get a really good sense of the data. You get a really good sense of the relationship and for other things that you might not have noticed in other ways. And that's one of the things we'll cover in this class, just something that I noticed as I was using it in this building this class and something that I was able to correct in the data that I noticed up until this point. So it's really interesting, really allows for a lot of detailed analysis, and there are some really good, you get lots of control over the different arguments that control the styling, the shape, the color of your plot. Okay. The line plot, the 3D line plot, is also a great one for really understanding the time series relationships. We're going to compare two time series together, understanding a really detailed analysis of that relationship. The chloropleth plot is really great for doing highlighting regional patterns. So if you wanted to say inspect the world or a globe or a country, this would be a good plot to highlight which regions have different values. Really, the only option when you have one of these plots, it's kind of more of a pretty unique situation where you need to do this, but when you need to, you have the chloropleth plot in Plotly. Okay, getting started with our 9th data analysis bootcamp class, going into hacker statistics. This is a little bit of a confusing class, to be honest with you. I'm not confusing in the sense it's a lot to take in. So it's really good that you once you practice with these concepts, and we're gonna show something in the last class when we talk about how to present these ideas that might help really understand this concept. So even if you don't understand it today, we're gonna show it in the next presentation how we use this concept in our data analysis and making our presentation. And so it'll make a little bit more sense, but it's really good to practice with this concept, but really appreciate the effect that randomness is having on our data. That's a factor, a feature in our data that we can't see. So it's really good to appreciate the amount of randomness that's included in our data. And so central limit theorem is a fundamental part to how hypothesis tests working, and we'll see it in action today. And it's one of those quirks of math that allows for some cool things, and we'll see how we use it today. So first we discuss randomness, really to get started in the sense that we, as I said, we want to appreciate this. We always want, when we take a sample of data, our goal is not to understand that sample, it's to understand the population as a whole. But we have randomness in our data. We don't really know, we didn't get the whole population, we got a random subset that is going to be different than our population. How different? You know, that's the question, right? It's there. We just don't know how different. And we need to do things to factor that. The understandings that we could be seeing could be just because it's a sample and not really different. And that's what leads into hypothesis testing. But we'll use hacker statistics today to visualize and really understand how hypothesis testing works. Okay. We just need to we just need to know that it's there, accept that it's there, and appreciate that it's there, that we have randomness in our data. We just can't see it. Okay, getting started talking about bootstrap resampling. This concept, if you've never heard about it, it's really about creating an independent version of your data set, a sample of your data set, to help simulate the randomness that happens as we collect the original sample. Okay, so the very important concept is that we're going to do bootstrap resampling with replacement. Now the idea is we're going to take we're going to take a ball out, like we have our child here picking balls out of the bag. He's going to take one out of the numbers 12, 18, 25, 30, 14. He's going to take one out, write down the number, and then put it back. And out of the bag again, he's going to draw another one, and write down the number, put it back. So you can see here 25, 12, 14, but then 25 again. Now the concept here is that he will be able to redraw the same row or the same ball again. Now it seems like a minor thing. It seems kind of silly too when you first hear about why would we want the same data twice. But what this does is it creates statistical independence. And what that means is because every ball that he takes is not dependent on what was already taken, the replicate that he creates is essentially independent of the original data set. Okay, and it works really well in simulating the randomness that would happen by the sampling process. So we can get a range of, instead of thinking of an average as a sample as this number, our average could be more of a range of data. Okay, so within these parameters. Okay, so continuing on with bootstrap resampling, we want to understand the process of how we're going to create our replicates. So as I said, we're going to use bootstrap resampling with replacement. We're going to take a ball out, write a number, put the ball back, and then withdraw again. So we're able to draw the same row twice or many times and miss other rows. Okay, so this creates independence because every time we draw a ball, it is not dependent on what was already taken. If we didn't have the with replacement, we'd essentially just get the same data set in a different ordering of rows, which doesn't really tell us very much, right? So what we're going to do is we're going to construct our bootstrap examples, and we're going to actually, bootstrap resampling with replacement to construct one data set of how many ever samples we choose. It can be more or less samples. And then what we'll do is we'll repeat this for many samples. So we'll construct many bootstrap replicates as we build our understanding of the randomness that's created by the sampling process. So recapping what we talked about, so we're going to go through the steps and create eventually a new bootstrap resampling with replacement, right? So we get our data, we do create a sampling, and then we're going to create a bootstrap replicate with replacement, calculate a statistic of interest, and then you don't really need to keep that bootstrap resample anymore, so we start over again. Okay, we're going to recreate as many bootstrap replicates as we want to understand how many averages, how many means, how many maxes, mins we're going to get to understand our data. Okay, so we're going to analyze bootstrap resampling, and then we're going to be able to visualize all these means, all these averages we've collected, and get a better understanding of really what each one includes, and really the variation in that final statistic that we'll get. Okay. So this really is the power of simulation, using Python to just bootstrap and really just in a Python loop to automate this simulation process of collecting our data, and we're able to then estimate the uncertainty that's just baked in our data set, right? How much would we expect this average or this correlation to deviate as we understand our data? A really interesting kind of quirk happens, a quirk of mathematics. I find these things really interesting, but they do exist. It's kind of like the gradient in neural networks. How if you just give your network an error, it seems to learn better, right? There's not a lot of, it's weird that the first person that figured out that quirk, but it's an interesting quirk and it works well to train neural networks. Same thing here. Central limit theorem is an interesting quirk of mathematics that allows us to validate how much uncertainty we expect in our data. Okay. So the idea is by random sampling, we're going to essentially, if you were to draw enough random samples and then plot the mean of the average, or plot the distribution of averages, min, max, any summary statistic will be collected and will distribute a normal distribution, will be in a normal distribution. Okay, so we're going to sample, collect averages. What will happen is the emergence of normality. So we kind of start to see, as we collect more of these averages, we'll start to get a more perfect normal distribution. So this happens regardless of the original distribution. If it was an exponential, abnormal, normal distribution, we'll get the normal distribution from plotting this. And this, because it's always going to be that same shape, we then are able to use hypothesis testing or hacker statistics to brute force the hypothesis testing to get a very similar answer to what our understanding of is the uncertainty in our data set. It's central limit theorem at work, and this is really just to kind of show what happens, how this actually happens. So if we have any distribution, if we were to sample, make 10 replicates and take 10 means of those replicates, we're going to get, a distribution that, can kind of look like anything. And then as we start doing collect 100, we start to see that emergence of normality happens actually quite quickly. And then you see 1,000. And if we were to do 1 million different means, so creating 1 million different replicates, taking the mean, this takes a little while to run, but we can start to see now that we get a nice, diverse spread out, essentially exactly like you would expect a normal distribution to look like. Okay, so this happens as an interesting quirk of math. This fact of resampling or sampling will always create, if you take enough samples, you will create a normal distribution for your summary statistic. Okay, and then we can gauge, based on what percentage do I believe that my statistic needs to be different enough from the mean to really say, yes, I think this is different. Okay? So although there are many types of hypothesis tests, we'll kind of keep it simple today. We'll talk about the two major types that you'll deal with. And so the one-tailed and the two-tailed hypothesis test. Kind of like these binoculars right here. They're looking at the same thing, but they're going to see it from different angles. They're going to see slightly different pictures when they look at the distribution of our plotted means that we looked at. Okay, so with the two-tailed test, we're testing if something is different than, so it can be above or below, and a one-tailed test is more just a greater than or less than. So two-tailed is for different, one-tailed is for greater than or less than. So kind of these two examples here, the new drug has a greater effect on the placebo, so the greater than symbol, or the two-tailed test, the new drug is different effect from the placebo, okay? And really, depending on what our problem is, we can define either one of these, and that will let you know and give you an insight of which one you're going to use. Okay, fairly simple concept, but just something to be aware of. Okay, so a really important concept to understand is the difference between a null and an alternative hypothesis. So the null hypothesis is kind of, I like this grumpy old judge right here is a good example. It's kind of what existed before. It was the accepted norm before. What was generally valid? What was the generally accepted principle before you want to try and introduce your alternative hypothesis, which is generally what you're trying to prove. I'm trying to prove that this drug is different, that this drug is better than what was before. Okay, or the old drug. Okay, and this is really, so the H naught right here is the null hypothesis. HA is usually the notation we use for the alternative hypothesis. And it truly is just good to write these out so that you're thinking about them as you're actually performing the test, because it can be a little bit confusing and you can get a little bit lost in them. Okay, so the null hypothesis, again, the grumpy old man, what existed before. The alternative, like the rising phoenix, we're just trying to introduce something new and changing to our generally accepted understanding of the universe. Getting into what hacker statistics really are is really, they're actually nothing super complicated. We're just going to use a loop in Python, and we're going to just repeat the loop as many times as we want to collect the sample. Okay, so we're going to loop, we're going to create a random sample, we're going to collect our statistic, save that usually in another list somewhere, appended to a list, and then we'll be later able to plot and analyze this list. So this concept is really, we're setting up an experiment in Python, and Python is just a really great tool. All coding language is a really good tool to automate this process. So what do hacker statistics tell us? So I think one of the biggest things that I've really found a lot of value in is that you're able to see the subtle differences. Okay, so although things might not pass a hypothesis test, visualizing things with the hacker statistics gives you much better understanding of, okay, well, maybe it didn't pass it, but I'm still noticing that there's a valid difference between these two categories. Okay, and this also creates allows us to create critical regions, or the p-values. Basically, what we want to say is we're certain that maybe our average or our correlation is within this range. Okay, and this gives us a good understanding of the data and how to work with it in that sense. Okay, and really appreciate it a little bit better than that 0.05, 0.06, 0.04. What do those really mean in terms of p-values? And then you can construct your own for what you would consider to be valuable. Okay, so recapping our mnemonics from this class. So we talked about randomness, how randomness is just a factor in our data set by the act of taking a sample. Okay, so it's just something there. We can't see it, but we need to acknowledge that it exists and the effect that it's having on our sample and the understanding we can extract in terms of insights. Okay, so we always have to be a little bit more cautious about our understanding with what an average is or correlation is. Okay, we can simulate this example and start to get an understanding of the randomness and its effect on our statistics by using Bootstrap resampling. This concept works by, if you were to have a bag full of numbers, you draw a ball with one number, you write it down, you put the ball back, and that's the with replacement part. Draw another ball and then write that number down. Okay, so you can build a list of any size this way with a different amount of samples, and you might draw some samples twice, or you might miss other ones altogether. This is very important that it's with replacement because this creates statistical independence from our data set, from our original data set. And so we can start to gauge the randomness that's occurring in our data set. It's so simple, but it allows us to simulate the effect of taking samples. Okay. So then what we do is we construct this replicate from our Bootstrap resampling process with replacement. And then we repeat this over and over again. So we construct one sample, we take a min, a mean, or max, and then we do this over and over again. We repeat this many times over. And really what we're doing is we're simulating the data collection process. Okay, so we're gonna create a Bootstrap sampled replicate, take a mean or a summary statistic, and then repeat this process over and over again. And then we'll be collecting these means, these averages, these summary statistics, and we'll be able to visualize this then in many different ways. Okay. We can also, a really interesting effect that happens is as we start to collect these summary statistics is they will always be in the normal distribution shape. Okay, it's very weird. It's called central limit theorem, but it really is this emergence of normality. So the more samples we take, we essentially get to be more normal distribution. Okay. As we keep collecting samples and we grow our sample size or our summary statistic size, we are going to get essentially normal. They're all going to look the same, right? There's going to eventually, the more and more samples we take, the more normal it's going to look, but it emerges very quickly as we start to simulate this process. The idea behind what we want to do is, or the reason that we can use this then in hypothesis testing, and what it's meant to accomplish is we're meant to validate what we're seeing in our data. Okay. So are we seeing something that's statistically different or not, right? We're validating, oh, this is the average of men and women, they're different. But is that really true, right? So we want to validate our data set. And what we want to do is we're going to use this to, do we focus on a one-tailed test or a two-tailed test? Okay, and this is really going to be looking at the same thing, but really we're going to be focused on slightly different questions. Okay. And that'll be related to, are things different or are things greater or less than, what's accepted, what's the norm of the accepted null hypothesis. Okay, and then so we get into null and alternative hypothesis, and this is really just how you ask the question. Null is going to be, it can be anything, but it's generally what was accepted before, kind of this old grumpy man, he's stuck in his beliefs, he's not going to be changing or anything like that. So we need to have an alternative hypothesis that has enough statistical proof that we can, that it is different, right? Like this phoenix rising from the ashes, we have a new idea, but we need to prove that we can't just say, it's different, right? We think it's good, but we need to really understand this using hypothesis testing to understand how robust that understanding is. Okay. So the way that we simulate this in Python is just through a simple loop, right? We're going to simulate the data acquisitions, the sampling process, and we're going to essentially allow us to visualize in the end our hypothesis test, which will give us a better understanding of, okay, so we got a 0.06 p-value. What does that really mean? How are my distributions really overlapping and how are they touching? Okay. So we use many mnemonics today in this class. I tried to connect things with colors, made the images unique, kind of painted little stories around them. We used color and word associations as well to help, give you another path back to each memory, each little tidbit of knowledge. Talked a lot about locations in 3D spaces when I was talking about the pictures. A good thing, there was lots of writing in this class that I didn't cover, so it'd be really good to go back and just reread everything, reread the notes underneath the videos, kind of another way to explain what we talked about in the videos. Okay, so this repeating and this recalling the knowledge and hearing it from different angles and stuff, from the videos, me talking, stuff in the presentations and the stuff below the presentations, the wording and little paragraphs below. It will help just lock this stuff in your memory, and hopefully you won't need to come back to these again and again. Okay. Thank you so much for joining me, and I'll see you for the Python workbook. Okay, and now thank you for joining me for the Python section of the 9th Data Analysis Bootcamp, Hacking Hypothesis Testing. So it's a really important class to really just, I think, understand this effect of hypothesis testing and resampling. When I was working for a fintech startup, we only had like 60 clients or something like that, a very small amount. And really, the only way that I was able to build a model, it just was not enough data to really be confident in anything. But through hacker statistics, you're able to really notice subtle differences and it kind of emphasizes them. And I was able to find out what is really important in making that decision. Okay. Okay. So I think this is a really important class. And if it's a little bit confusing, I think it just requires you to practice with it a little bit and play around with this concept. It's why I introduced sampling in the first class. And we're kind of coming full circle, is to highlight, the things that we learned in that class, the effect of sampling. Okay. And then how hypothesis testing is works in that same concept. We're able to use that to get a more robust understanding of our data. Anyways, I'm gonna stop rambling. So here what we have, I'm doing a little bit of different stuff with Python or Seaborn today. So I create a palette, get bored of the normal standard colors right here. So just create another color or palette, and colormine.io is a great place to go to get a different color palette. And here I'm going to do set palette. So this is actually what's setting the palette right here. I don't need to do these two lines. I just like to actually see what my palette is. So sns.color_palette. It's going to give you the ability to look at and see kind of how your palette is set up, and if you like to kind of move things around or change things around. Okay. I'm going to use this set style as well. So we're able to do a lot of changing on Seaborn using the set style. And this is a list of kind of everything that there's available. Here's a link to other things that I wasn't able to include. And so axis.face color, we're going to do this face color. Figure.face color, we're going to do this face color. Text color, we're going to do this. Tick color, we're going to do this. Tick color, edge color, and so on. Everything where we have the ability to change. So it makes them for some pretty cool plotting. Okay. So here what we're going to do is define our own little hist plot function that allows us to do kind of more for an effect in any sense. Okay, so in the plot_hist function that we're creating, so the first thing we're going to do is do subplots. In the next step, what we're going to do is ax equals sns.histplot, data equals array, and alpha equals 0.8. Okay. What I'm going to do next is I assign this to an object. So I'm going to go for rectangle in ax.patches. It gives me a list of all of the items in my plot, and we're going to iterate through that. I'm going to iterate through and make the line width of the rectangles a little bit thicker on the outside and change the edge color to a different color. Okay. I'm going to add a title to my plot, label none, and plot title layout. Okay. So this allows you to kind of repeat this, so I don't have to do the same. It's not a lot of code, but you could do that in every cell, but a little bit nicer and neater to just plot it right here. Okay. And so my uniform distribution. So what I did is I randomly sampled from numpy.random.uniform, and this is where I use numpy a whole bunch, is this random function. It's amazing how much you need random numbers. So numpy.random.uniform, 1 to 100 sample size is the sample size that we set up here, so 500. Okay, and then I'm just putting this into a series, and you can see it looking right here. Okay, and if we do plot, not plt, plot_hist samples uni, the samples that we just created right there, get a uniform-ish distribution, and a little bit of random deviation will change that, but basically a random distribution of from the uniform distribution. Okay. So what I'm going to do here is I'm going to get samples means. Okay. So this is now plotting all of the sample means from this distribution. So I'm going to go ahead and I'm going to go make a blank list of means. I'm going to go for range underscore. So this means I'm not using this down in that for loop right here, just to signify that I'm not going to use this. for in range means. So I'm just going to repeat this 100 times. Okay, so how many n means do I want to collect? The number, essentially samples, I guess you could say I want. Okay. In the way I'm going to randomly sample this, I'm going to use numpy.random.random integer, because if it's an integer, I can use that to logically index, or not logically index, just index into my data frame or my numpy array. I'm going to go from blank to the number of values that I have in my array, size equals sample size, okay, which is 200. And then I'm going to append, I'm doing a couple things right here. I'm going to select the values from this index based on an array. And so this is the way that you can select index values from an array. It's just these square brackets right here. Normally in pandas, just if you remember, it'd be dot. Okay, to do this, it's not pandas and numpy, right? Data types, we got to pay attention to those. And so a numpy array, and then what we're going to do is we're going to select random rows. We're going to get the mean of those rows, and then we're going to append this to the means list up above. Okay, then I'm going to create a figure. I'm going to then do x.histplot and putting the data, the means, the alpha 8. And then what I'm going to do is 4 rectangular patches, the line width, the edge color, give it a nice kind of like white edges. Trying to be fancy. Show you guys everything you can do with Seaborn in this lesson as well, side lesson. Okay, then putting the plot in with the title of the plot, the uniform right here, no Y label, tight layout. And tight layout is just going to make sure everything sits nice. It's not necessarily going to make it tighter, but it's going to make sure everything's kind of sitting spaced out nice and stuff. It's always a good idea to do, especially when you're doing more advanced stuff like this, but it's more so when you're adding a few things in the plot would be the most appropriate time, but this still works here. Okay, and then plot. So now we can, every time we run this, it should be a little bit different. Sometimes a lot different, sometimes a little bit different. But notice it's almost always, see if we did 5,000. And it gets closer to that normal distribution the more samples we take, right? And so this is coming from a uniform distribution. Just wanted to show that if we do the same thing from a normal distribution, also going to get a normal distribution, no surprise there. We only took 10 samples though, you know, even from a normal distribution, 100 samples, you know, it's starting to emerge, but it wouldn't really call that normal yet. But as we get to 1,000 samples, it really starts to take on that normal distribution. At 1,000,000 samples, and it's perfectly a normal distribution, which is just really interesting. This is the concept of how we can use hypothesis testing. So it's going to say at a certain level, we can be 5% sure that it's caused by random chance, that this is, you know, we got the average one time and it was right here, but sometimes we'll get an average and it'll be over here, sometimes it'll be over here, sometimes it'll be over here, sometimes over here. So if you get an average that's right over here, you can be sure that it's so far out of the middle of this distribution from the accepted mean, you can be that it's so far outside of the generally accepted mean from before and your null hypothesis. And if you get an average over here, this is going to say is, well, I'm, you know, sure that this could only happen 1% of the time because of random chance. And so it's likely that I'm going to believe these results. That it's not very unlikely that it was just random chance, especially if I was diligent in how I collected my sample. But you can see again, this is how we would use it. But because of this shape of the central limit theorem, where we get the normal distribution from resampling, which is super weird, but it works really good. It's kind of cool that we can do this. And then just to show, I'm going to get an exponential distribution, random. There's different types of exponential distributions. The one that we normally talk about is the standard exponential and exponential distribution. And then as you get the simple means from it though, just a normal distribution again. Normal distribution again, or merging already. If it was abnormal, what I'm going to do is numpy.concat. I'm going to concat the two distributions together. Then what we would do is plotting the normal distribution. You can see abnormal. If I sample from that, even, well, after 10, it's not so much, but 100, start to see something of a normal with an outlier. But 1,000, you can really start to see that normal distribution emerging. Okay, and it's really kind of cool that we get that normal from an exponential and abnormal, really weird looking distribution. We can get the normal distribution at the end. Okay, and then again, so now let's try this on a data set. Let's play around with this and see if we can notice the subtle differences between, we have a sex column in this, we have a population column. So between two different categories here, and if we can really start to notice between sex and population, there's differences in any of these features. So more than just getting the average and saying, okay, well, the average is different. You can see here, skull width, 56, 57. I don't know if you can really statistically say that any of these, because it could just be random chance, right? You could have got a random sampling of females that just caused your average to be a little bit more to one side or the other side. And so you really can't statistically say that, I'm looking at this, that any of these really are actually different. But is that really true? So let's look at this in a little bit further. Okay, so we looked at by sex, by population. There is, I'm just trying to remember if there's one foot length was one of them that was quite different. But that's about it, which is really interesting. Okay, so I'm going to redo the plot histogram with a data frame this time. Just a slightly different value here. So what we're going to do is we're going to go plot the histogram with the df with the data frame this time. The x value is the value that we'll be giving it right here, and then patches is the same, title, no y label, and tight layouts. Okay, so if we run this, plot history right here. Okay, so define the skull width by sex. You can see they're pretty overlapped, right? Nothing really too surprising there. And then total foot length, you can start to see a little bit of a difference here. And then population foot length. And we saw that was one of the bigger ones by population. So it's the most distinct differences. There's still a lot of overlap though. So the thing is this likely would not pass hypothesis test, because you could easily say that more than 5% of the data is, they're overlapping, especially with this over here. So can we get a good sense of, we'll play with this today and you can see ear conch is quite different. That one's maybe a little bit easier, but we'll play with this and see if we can really tell the subtle differences and become a little bit more confident in this through hypothesis testing. Okay. So null hypothesis, it's always a good idea to write them out, truthfully. Okay, so null hypothesis is skull width is the same. And that's the generally accepted kind of boring principle that was there before. You're trying to change this concept like the phoenix rising from the ashes to make sure that, we're trying to say that something is different right here. So then is lower than the male. The way that you would do this in, I guess, classically is using stats model dot stats weight stats z test right here. Run the z-test on this mean. So I'm going to get the mean of the males, and then what I'm going to do is I'm going to say the female distribution right here, logically indexing, selecting the value column and saying value of mean, and I'm going to say that it's smaller, okay? So now it's interesting, we get a 0.05, okay? That's nice, 0.05, so it's not technically, we wouldn't technically pass that, but let's see if we can inspect this a little bit more, because I feel that, there's probably a good difference, right? It's just didn't pass, right? So 5.1% of a chance that it's random instead of a 5% chance. So, but as you plot this, really, you're kind of getting that sense that, it really doesn't seem like they are different, right? And so let's see this with hacker statistics, okay? So if we look at this, what I'm going to do, just to highlight what I'm going to do first, I need this to do the colors in the legend. So I'm just going to create 2D lines. I'm going to create two colors from this, color palette 1, 0, and 4, and putting it into this. Okay, so it's creating custom lines that I'll use then in my legend, just to kind of make everything line up. Feet and skull width right here means 1. I'm then going to do mean right here of the one distribution. I'm going to get 1,000 samples. I'm going to append all of those samples to means 1, and then I'm going to plot that data after I make a figure, plot the data, and we're going to go for rec, and then we're going to do the outlining of the bars for rec and AX patches. Then I'm going to do the mean from above and plot the vertical line. Okay, plt.title, y label none, legend right here, and this is where I'm adding those two colors for my custom lines, and then labeling the plot is because I did two plots on top of each other, so you can't just call the legend and it'll work, unfortunately. We had to put a little bit, because we're doing kind of a little bit of an interesting thing here. Tight layout and then show. Okay, so I just wanted to show, making that step by step. It's not so bad. Okay. So you get that distribution right here. To do a little bit further though, so this is just plotting it right here. Okay. Oh, gotta make sure you run everything. Okay, so we get our little distribution. You could say it's not, there's probably more than 5% of the data over here, so it's kind of, it's not really, it is different, but it could not be as well, right? So, okay, so getting into how we'll build the this plot, a little bit of bootstrapping analytics here. Okay, so or hacker analytics, I guess you could say. So if we're gonna do this, we're gonna do the sample collecting of the means, but we're gonna do that 100 times. Okay, so what we're gonna do is we're gonna collect 80 samples of 50, and then get the index numbers. Select the index numbers. This is using pandas though, so just to highlight that, I'm gonna reset the index just to make sure it's 0 to whatever number, because I'm logically indexing it, so it would be kind of a broken ordering of numbers in terms of that, because we're just going to get the ones that are female. I'm going to reset that though, so I can then randomly sample just the index values based on the length. So 0 to the number of rows, and that will be the index values that I'm going to select from that. Okay. So then I'm going to get the mean and append that to the means list right here. Okay. I'm going to plot that right here. I'm going to do the patches that we've seen before. I'm going to add I'm going to create a big list of the sample means right here. And then the very end, I'm going to plot the mean from the original, the alternative distribution. Okay. And then everything else, I guess the title, set label, custom lines, tie layout, and show are all the same. Okay, and so as we look at this, you can see there's quite a nice little tail right here. Quite a long little tail, but they're very really likely outliers that are causing the situation. So sometimes the males or the females are larger, but this could be like an outlier situation. So it doesn't really seem like there's a lot of data or a lot of means over here to really support that it is larger, right? So we saw that it barely failed the hypothesis test that females are smaller than males. And I guess you can kind of see it, but you get a better understanding now of the hypothesis test. Where did that number come from, right? So what's kind of cool is we can go all sample means to greater than mean, and so greater than this, and we can see all sample means. So there's only 5% right there. So again, it's very interesting now. We got a very close answer to what we got when we did the hypothesis testing. So we're able to brute force this and now visualize this. And okay, yeah, so it failed it, but I'm still actually going to be pretty confident though. There's going to be some random females that are quite large, but most of them in general are going to be smaller than the population of males, would be what I would expect if I would go there. Okay, so again, a very, very close score between the two. Now we're going to put that whole function that I did up here into, or sorry, the whole thing that I did up there into a function. So you could see that was very long. So I just did the exact same thing and put it into a function. And if we plot this right here, dun, dun, dun. It takes a little while to do these ones. Okay, and so there you can go. We see the whole plot now done like this with our plot, all in a little nice clean one line of code. Well, a few lines of code, but a nice little function that we can just keep our notebook clean. Okay, so I wrote a little bit about what to interpret from hacker statistics. Go ahead and read this after. I'm not going to read this to you in the video, but you can go afterwards and read through this and get a little bit more detail. I know this is confusing the first time you see it, but as you keep using it, you'll start to get a better sense of really what hypothesis testing is, what sampling causes, and what you can believe in when you take a summary statistic, how much you should believe in that summary statistic. Okay, so looking at the females here, and what we're going to say is males and females are the same length. Okay, so just going to do a two-sided test now when we do the z-test from stats model that we imported up above, and we say 0.1, 0.01. So no, I would not say when you look at this that they're any different at all. Okay. So we look at the hypothesis test. Foot length is different than population. So let's look at this, and we can see that it looks quite different when you plot it. And you can see you got a very, very low p-value here. Okay, so just looking at the more traditional way to do hypothesis testing here as well. Okay. Looking at a two-sample test, so looking at the total length, population, class 1 and class 2. So highlighting what those are, Vic and other. I do it like this because I know I'm going to put this into a function afterwards. So if I have my arguments right up here when I'm writing this, it'll fit very nicely into a function when I put it down here. Okay. So make a plot. I'm going to do two samples though, because I'm going to get two different distributions instead of just one this time. Okay. So we're looking to see if two distributions are different. Okay. So ear crunch is different by population. Okay. Smaller or larger, but just different. Okay. And so here we're going to do our index 1, index 2, sampling those sizes. Then we're going to reset index and sample from that index. And then plotting two different histograms right here. And then after I plot both of those, they'll be in the same plot. So then I'm going to iterate through the rectangles, change the line width of those, and then set title, Y label, legend, and then type layout and show. Okay, so doing all of those. So now we get a sense that they look pretty different. It's true. There's still a lot of overlap, but you're getting to see that little smaller tail that kind of comes out right here. And really the blue kind of just truncates. It just kind of seems to end right here. Sometimes I don't really see any boxes that go any more than that. Okay. Throwing that all into a function. Okay. So we looked at ear conch by population in Vic, you can see. Okay, and you can see, well, that was pretty easy there. They're pretty different right there. And then we collect the averages. Okay. And then total length, what does that look like? So now here we're getting the total length here, and you can see, really, I mean, even the thing is, we could see that the populations were a little bit different, especially by foot length. But really here you can see that sometimes the means of ones is even lower than the other side, right? So, I mean, it's very easy to see that these are not statistically different right here. You got the mins are basically the same, just a little bit on the outside on one of them. The maxes are, again, sample 1 and sample 2. They're very close to the same. You can see here 91 and 89. So we got them very, very close. So basically these distributions to me would be overlapping. And if we look at this in a p-value, you can see you get a 17% p-value. I would actually put that up at higher, that they're from the same distribution, truthfully, after looking at this and understanding the actual hacker statistics, how these are going to plot out. If that's only 17%, that would surprise me. It gives me more confidence here that there is no difference, right? 17% chance that they're from, they are the same. I'd say it's a lot higher than that, truthfully. And so that's kind of the idea here, is we're just getting a better understanding. So, and you can see again a little bit more about how to understand p-values here. Okay, so thank you so much for joining me. I know that was a little bit of a confusing class, but go through this, play around with this, and we'll use this in the next class to help us highlight some subtle differences that we weren't really able to find in any other way. Okay, so thank you for joining me, and I'll see you for the data analysis bootcamp number 10, and we're in the home stretch.